Imagine a fire breaks out on the 40th floor of a modern, towering skyscraper high above the city streets. In this stairwell diagram, we see the core limitation of ground-based firefighting. As a fire hose winds upward, friction loss and gravity's sheer weight cause the water pressure to plummet to zero long before it reaches the blaze. To bypass this physical limit, engineers have to build permanent vertical pipelines directly into the architecture. Depending on exactly how tall a building is, architects rely on two entirely different systems to solve this problem: dry risers and wet risers. As buildings reach further into the sky, the structure itself has to serve as the primary firefighting weapon, determining the outcome of the blaze before the fire brigade even arrives on the scene. In the UK, building codes dictate that any structure taller than 18 meters, but under the 50-meter mark, typically requires a dry riser. A dry riser is exactly what it sounds like. Under normal conditions, this vertical pipeline remains completely empty, sitting at normal atmospheric pressure. When an emergency happens, the workflow starts down at street level. Arriving fire engines connect hoses directly to a specialized external access point, called an inlet breeching. In this cross-section schematic, the fire engine uses its powerful pumps to charge the system, pushing high-pressure water vertically through the core and instantly filling the empty pipe. Bypassing the stairwell climb, firefighters carry short hoses to the burning floor, connecting directly to an outlet branching off the main pipe, called a landing valve. Accepting a brief delay to fill the pipe with water, dry risers deliver massive operational speed, eliminating the exhausting process of dragging heavy hoses up dozens of flights of stairs. But there is an absolute limit to how high an external fire engine can push water, the 50-meter mark. Once a building exceeds 50 meters in height, it must utilize a wet riser system, which is permanently charged with pressurized water at all times. This requires serious mechanical complexity, as shown in this flow logic diagram. The system relies on massive on-site water storage tanks and a dedicated internal pump set, featuring duty, standby, and jockey pumps, constantly circulating water to maintain pressure. The advantage is speed. Firefighters have instant access to water the second they open an upper floor landing valve. However, all that vertical water creates extreme static pressure. To fix this, pressure regulating valves, or PRVs, step the extreme pressure down to a safe 8 bar, making the hoses manageable. Wet risers completely shift the burden of water delivery away from the responding fire engine, relying entirely on the building's own autonomous mechanical engineering. To ensure safe access during an evacuation, both wet and dry risers are strictly located within a building's protected firefighting shafts and fire-resistant stairwells. Because they are hidden away, you have to look for specific mandatory signage to locate dry riser access points in an emergency. Likewise, you will find equivalent, clearly marked signage required for all wet riser access points. But these hidden lifelines face a silent threat: electrochemical corrosion. Inside the supposedly empty pipes of a dry riser, the mix of oxygen and pooled water creates the perfect environment for deep orange rust to bloom, eventually eating pinhole leaks straight through the steel. Wet risers have their own unique vulnerability. If their water-filled pipes run through uninsulated shafts during winter, the water can freeze. Freezing water expands with immense force, which can shatter valves and rupture pipes. Because these systems exist in hidden, hostile environments, routine neglect can easily transform a building's greatest lifeline into a deadly failure point. To prevent that, building managers must follow a mandatory visual inspection protocol every 6 months, checking for vandalism, stolen brass caps, and obvious leaks. They also undergo an intense annual hydrostatic pressure test. A hydrostatic test is a procedure where the pipes are filled with water and pressurized, in this case, forced to hold up to 12 bar of pressure for 15 minutes, to guarantee absolute structural integrity. Despite their completely different mechanics, the ultimate purpose of both systems remains identical: delivering rapid, reliable fire suppression at high elevations. Whether relying on the atmospheric simplicity of a dry riser or the heavily pressurized complexity of a wet riser, actively maintaining the physics of elevation is the only true way to secure the modern skyline.